Section 5.1, Fundamental Identities. In this video, we will be looking at how to simplify trigonometric expressions using the identities and properties that we have learned. To go back through some of these identities, we'll look at the fundamental identities first. The fundamental identities, these are the 8 identities that we should become very familiar with. The first 5 we definitely should remember. Reciprocal identity, your cosecant of theta is equal to 1 over sine of theta. Secant of theta is 1 over cosine of theta, and cotangent of theta is 1 over tangent of theta. We also have our quotient identities. Tangent of theta can be rewritten as sine of theta over cosine of theta, and cotangent of theta is equal to cosine of theta over sine of theta because they are reciprocals of each other. We also have the Pythagorean identities. The Pythagorean identities, we established these identities earlier on. The first one, sine squared plus cosine squared, is equal to 1. And then the other 2 are basically derived from that one. So if we take the first identity and divide by cosine squared to both sides, you will get tangent squared. Sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. And then 1 divided by cosine squared is secant squared. So we can always go back and reestablish these identities, the Pythagorean identities, so we know what they are. The third one, we can do the same thing. We will take the original, but now we will divide by sine squared. So if we divide by sine squared of theta, sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent. And then 1 divided by sine squared is cosecant. So once again, we can establish these last 2 identities from the original Pythagorean identity. Sine squared plus cosine squared is equal to 1. So once again, these are the 8 fundamental identities. The even and odd properties we have discussed as well. So the even and odd properties, sine and cosecant are odd properties, and odd properties are symmetric to the origin. And so if they're symmetric to the origin, then sine of negative theta is the same thing as negative sine of theta, and cosecant of negative theta is equal to negative cosecant of theta. Tangent and cotangent are also odd properties. So tangent of negative theta is negative tangent of theta, and cotangent of negative theta is negative cotangent of theta. Cosine and secant are even, which means they're symmetric to the y-axis. So cosine of negative theta is equivalent to cosine of theta, and secant of negative theta is equivalent to secant of theta. So those are your even and odd properties. We also have cofunction identities. These are your complementary angle theorem. So sine of pi over 2, which remember is 90, minus angle u is equal to cosine of angle u. Tangent of 90, or pi over 2 minus u, its cofunction for tangent is cotangent, so cotangent of u. And secant of pi over 2 minus u, its cofunction is cosecant. All right. And then we can go the other way. Cosine of pi over 2 minus u would be equivalent to sine of u. Cotangent would be equivalent to tangent of u. And cosecant of pi over 2 minus u would be equivalent to secant of angle u. And once again, we have talked about all these identities and properties, so if they're not making sense as to where they came from, you can always go back and watch those previous videos. So now what we're going to be doing in this chapter is we're going to be using these identities to simplify and eventually establish new identities. So on this first one, we're just going to use the identities to start simplifying these things. So for example, on example 1a, cosine of pi over 2 minus x is your cofunctions, that is your complementary angle theorem. So cosine can be rewritten as its cofunction sine of angle x. And then sine of negative x here, that is your odd property for sine, so that means the negative would come out front. So it'd be negative sine of x, and then sine of x divided by negative sine of x. The sine of x is canceled, and you're left with 1 divided by negative 1, which is negative 1. On the next example, we have 1 minus sine squared of x times secant of x. So 1 minus sine squared of x looks like the Pythagorean identity. I'm going to go back to our page for the Pythagorean identity. Take a look at your Pythagorean identity, that first one. It's sine squared plus cosine squared is equal to 1. But if that is true, and I subtract sine squared to the other side, then that would be equivalent to cosine squared of theta. If I subtract cosine squared, then that would be equivalent to 1 minus cosine squared of theta is equal to sine squared of theta. So these two are directly related to the sine squared plus cosine squared of theta is equal to 1. So if we see either one of these as well, we can also use this one. So we had 1 minus sine squared of theta, so that's equivalent to cosine squared. So we can rewrite this using Pythagorean identity as cosine squared of theta times secant is the reciprocal of cosine. Now I said theta, but we're actually using x right here, so let me get rid of theta and change that to an x. So cosine squared of x. And then now we can simplify this. We have cosine squared of x divided by cosine of x. So one of those would cancel out, and that would leave you with cosine of x. All right, let's take a look at the last one. We have cosine of x times sine squared of x minus cosine of x. We notice that cosine of x is in common with both terms, so let's go ahead and factor out the cosine of x and see what we have left. That would be minus 1. So sine squared of x minus 1. All right, well, sine squared of x minus 1. Let's once again go back, because it's a little different than 1 minus sine squared. If we go back to our Pythagorean identities, we don't have a sine squared of x minus 1. We do have a 1 minus sine squared. So can we take sine squared of x minus 1 and factor out a negative so that we can get what we want? That would be a positive 1 now minus a negative sine squared of x. And so now, by doing that, 1 minus sine squared is equal to cosine squared. And so cosine squared of x times cosine of x would give you, and don't forget the negative, negative cosine cubed of x. So you can see that, we're definitely using the different identities and properties to simplify each of these expressions. All right, on this one, we're going to work on factoring and using the fundamental identities to simplify when we can. So if you notice on A, you got 2 cosine squared of theta minus cosine of theta minus 1. You can leave it in that form, or if you want, you can rewrite it by saying that x is going to be equal to cosine of theta. And this will just help rewrite the quadratic in a more familiar term, or familiar way. That would give us 2x squared minus x minus 1. And so now if I ask you to factor, you have 2x times x, and then factors of 1 are 1, but you need a middle term of negative, so make the first one positive and the second one negative, and you can check that and see that it works. But we don't want to leave it like this because we know that x is actually equal to cosine of theta. So we're going to replace x with cosine of theta. So it's 2 cosine of theta plus 1, and then cosine of theta minus 1. And that's really, we can't do anything else in terms of those two binomials. So that's as far as we're going to go on that one. You don't have to use the x equals cosine theta, but if it helps to rewrite it in terms of x and then to switch it back, that's perfectly fine. All right, on the second example here, we have secant squared of x minus tangent of x minus 7. Now, we have secant and tangent. So is there a way that we can rewrite one of those so that we have the same trig functions? Secant squared of x is one of our Pythagorean identities. So we can rewrite secant squared as tangent squared of x plus 1. So that replaces the secant squared. And then we have minus tangent of x minus 7. So let's combine our like terms. We have tangent squared of x minus tangent of x, and then minus 6. So we can do the same thing we did a second ago. We won't use x as our unknown because we have tangent squared of x, so let's just pick a different variable. We'll go with a is equal to tangent of x. So we're trying to factor a squared minus a minus 6. And so you can see that'll be a minus 3, a plus 2, and then once again we'll rewrite it back in tangent form, tangent of x minus 3 and tangent of x plus 2. And so once again we can't do anything else with that, so we'll leave it in that form. Alright, let's take a look at this last example, 2 minus sine squared of theta minus sine to the 4th of theta. So on this one we're actually going to let x equal sine squared of theta, so that when we go to rewrite it, it will be in quadratic form, so it would be 2 minus x squared. And so we can factor this. Let's see what we get. So we got 2 and 1, and then we need the x squared, so we need an x and an x, one of them being negative. We do need a positive 2 but a negative middle term, so once again you can double check that, and that should work. Now we will plug back in what we know for x. It'll be 2 plus sine squared of theta, and then 1 minus sine squared of theta. And so what you notice is we have 1 minus sine squared of theta, so we can actually rewrite that one using our identities. So this will be 2 plus sine squared of theta, and then 1 minus sine squared of theta is equal to cosine squared of theta. So that one we were actually able to take one of the factors and rewrite it as another one of our trig functions using the identity. So 1 minus sine squared is equal to cosine squared. And that's really as far as we can go with that one. So once again on this example 2, just working on some different things with factoring and kind of going from there and just trying to simplify it as much as we can. So go ahead and try example 3 on your own. I want you to perform the multiplication, so you're taking a binomial times a binomial, and then use your fundamental identities to simplify once you multiply it out. So go ahead and pause the video and see if you can do this one on your own. Alright, you can see that I multiplied the two binomials together to get cotangent squared of x minus cotangent x cosecant x, and then plus cotangent x cosecant x minus cosecant squared of x. So the middle term cancels out as the difference of squares. You're left with cotangent squared of x minus cosecant squared of x. Looking at that, it looked like a Pythagorean, so I went back to my Pythagorean identities and noticed I had one written as cotangent squared of theta plus 1 is equal to cosecant squared of theta. So we can manipulate that one by just subtracting the cotangent to the other side, but that would give me cosecant squared of theta minus cotangent squared of theta. So I then factored out the negative 1 to get cosecant squared minus cotangent squared. And then that was equal to 1, so then negative 1 times 1 was negative 1. So once again, continuing just to work on these identities and just manipulating and simplifying expressions. Alright, on the next example, I want you to add or subtract and then use the identities to simplify. So when you add or subtract, you need a common denominator. So once again, pause the video and see if you can work through this one. Alright, you can see I found a common denominator. I needed to multiply the left side by 1 minus sine of theta to top and bottom, because that was the part that was missing from the second equation, or that's not the equation, sorry, the second expression. And then the right-hand side of the sum, I multiply by 1 plus sine of theta. So I created the common denominator of 1 minus sine of theta and 1 plus sine of theta. So I had 1 minus sine of theta on top here, plus, on the other side, 1 plus sine of theta. And so I rewrote it with my common denominator, and then combined those two together, which canceled the sine of theta, and then 1 plus 1 was 2. I then multiplied the two denominators, sorry, not the two denominators, but the denominator, the two binomials together, to get 1 minus sine squared of theta. And then I simplified 1 minus sine squared of theta to cosine squared of theta, because this, once again, is your Pythagorean identity. And so 1 over 1 plus sine of theta plus 1 over 1 minus sine of theta can simplify all the way down to 2 divided by cosine squared of theta. So on example 5, what we're finally getting to is what we want to do for most of the part in this chapter that we're working on, is we want to verify the identity algebraically. So we want to basically prove that secant of theta times cotangent of theta is equal to cosecant of theta. Now when you do that, you can only manipulate one side at a time. So pick the more complicated side, which is probably secant of theta times cotangent of theta. Use your identities to simplify it. So secant can be rewritten as 1 over cosine of theta. Cotangent can be rewritten using the quotient identities as sine of, not sine, other way. We will do cosine of theta divided by sine of theta. And we're trying to get that to equal cosecant of theta. So you can see that your cosines will cancel out and leave you with 1 over sine of theta is equal to cosecant of theta. And then 1 over sine of theta, we can use the reciprocal property to say that that is equivalent to cosecant of theta. And so therefore cosecant of theta is equal to cosecant of theta. So we just verified or proved that secant of theta times cotangent of theta is equal to cosecant of theta. Alright, and the last thing is, when we're doing identities and we're saying that two things are equivalent to each other, we can verify the same identity numerically and graphically. And we've done this before with other things. So secant of theta times cotangent of theta is equal to cosecant of theta. So if we plug in secant of theta times cotangent of theta, but we got to do it in terms of sine and cosine. So that's the top equation. And then we take the other equation, or the other side of the equation, cosecant of theta, which is 1 over sine of theta. And if we plug both of those in, and you look at it numerically, you should see that the values are equivalent across the table. So if that is true, then we're verifying that they are equivalent. And then graphically, you should see that the same graph will overlap on each of those. They should be exactly the same graph. Just make sure you set your graph in radians so that you're able to see those graphs. So this is just a nice way on your graphing calculator, once again, to kind of prove that two things are equivalent. You can either look at the table, which is probably the best way because you can see all those different values, or using the graph to make sure that it overlaps. So we covered a lot of different things here, but once again, really looking and focusing on those identities that we have learned and being able to apply those identities and use them to simplify expressions into different simpler terms, or being able to eventually prove that two identities are equivalent to each other. So write a quick summary about the things that we have discussed in this lesson.